And good afternoon again. Thank you everyone for attending today's webinar, Developments in Precision Positioning Stages with High-Speed Range, brought to you by Design World Magazine. We would like to thank our presenter, George Jaffe of Steinmeyer, for being here today. I'm Leslie Langnaw, Managing Editor at Design World, and I'll be your moderator today. Just a couple of housekeeping details before we get started. If you wish to tweet about this webinar anytime during or after, use the hashtag #DWWebinar. We will have a question and answer session after the presentation, but you can go ahead and submit your questions and we will ask them after the presenter has finished. Questions can be asked using the GoToWebinar area on your screen. Now, I would like to introduce our presenter. He is George Jaffe, Executive Vice President for Steinmeyer, Inc., the U.S. subsidiary of the Steinmeyer Group. He is responsible for engineering support of precision linear and rotary motion systems and ball screws in North America. He has been involved in this field of linear motion for 35 years as a systems design engineer, engineering manager, and product manager. And he'll answer the questions after the presentation. So without further ado, I'm going to hand over the mic to George. George?
Thank you very much, Leslie. Appreciate the intro, and thanks for everyone chiming in and listening to this presentation. Just a brief word on Steinmeyer before we get into the slide presentation. Steinmeyer is a global leader primarily known for ball screws. We are the largest manufacturer of ground ball screws in Europe and offer the largest range of anyone in the world, from 3 millimeter diameter up to 160 millimeter in diameter. We also make stages. A part of Steinmeyer Group is involved in stages, and that's the subject that we're going to be talking about today. Specifically positioning stages for those applications with what we would call extremely large velocity range, and it's a development. It's a product that Steinmeyer has developed specifically for to address some issues in the field of positioning. So let's see if okay, here we go. Sorry about that. Okay. So basically, the presentation will be in 5 parts. The first thing we're going to do is describe the problem itself. Then we're going to move on to describing what we view as the current state of the art. In other words, what's the current state of solutions to this issue. Then we're going to introduce a new approach to the problem, follow it with some results of some field tests, and then discuss some applications. So the description of typical requirements for such a stage. Clearly, we mentioned that we're seeking or the application requires a relatively high dynamic velocity range from extremely slow to fast, and we'll define that shortly. And you can see that in various applications in the measurement, primarily in the measurement field, microelectronics, inspection arena. The stage also requires relatively high accuracies for positionings, typically in the submicron range, with repeatabilities to typically less than 100 nanometers. And also, here's the key, long travels could be up to 300 millimeters and maybe even more. So another way to look at this, and you'll notice that curiously enough, we've provided an image of also another high-performance German product, a Porsche, and that has a speed range in the neighborhood of 1 kilometer per hour up to 300 kilometers per hour, or roughly a ratio of 300 to 1. On the right-hand side of the screen, you can see another precision product. In this case, it's a stage, and typically that speed ranges from 50 microns per second, 0.05 millimeters per second, up to 100 millimeters per second and more, or else, in other words, a dynamic range of 2,000 to 1. But suppose the requirement is considerably greater than that. Say it's 10 nanometers per second up to 100 millimeters per second. In other words, a dynamic range of 10 million to 1. So the question is, how does one go about doing that? The current state of the art generally offers three possibilities. The first one is fairly conventional, ball screw driven by a DC motor or a stepper motor. And the advantages are that it can be used in any orientation, especially vertical. It is certainly cost effective, and it's a very production-tested principle and robust design. The disadvantage is that it's a relatively low dynamic range in the neighborhood of 2,000 to 1, which certainly can address the certain areas of speed. Another possibility is direct drives, whether they be conventional linear motors, electromagnetic, or piezo linear motors. These are still relatively cost effective. They can achieve very high accelerations and velocities, and certainly don't exhibit any drive wear because they're non-contact. At least the electromagnetic linear motor is. It's not necessarily true of piezo linear motors, but that's a subset. The disadvantage is that they're not very suitable in vertical usage, and that's because they typically require a brake. And also, especially in vertical usages, because of the power you need to maintain position, they generate a lot of heat. The third possibility is a piezo stack, and certainly the advantages there are you can get travels down to sub-micron range, but the disadvantage is typically they are very short travels, typically on the order of hundreds of microns, maybe up to a millimeter, but that's about it. Closed loop is difficult in this. You tend to get position drift, and the power required is on the high voltage end. So here's another view of the current state-of-the-art solution to the extremely large velocity range, and we ascribe this as being, if one stage doesn't work, use two. And this is an example of one solution where you have a lower XY stage, in this case a ball screw driven stage, and then above it you have a piezo stack. So you've got the XY ball screw system achieving the high velocity, and when you switch to low velocity, high resolution, you switch to the piezo stack system. So what's the limitation, or what are the issues here? Basically, you've got two stages, two systems, so you end up having discontinuous positioning, and with typically lower system stiffness. You've got duplicates of everything. You've got two force generators or two drives, two measuring systems, two controls. You have a piezo stack system, which is sensitive to shock and overload. And then because of the dual nature of this thing, you've got high costs. The other disadvantage of this is that you've also got higher errors because you've got dual linear bearing systems. Here is a different approach, a new approach, and one that has been patented by us. I do apologize for the distortion in the image that happens when you transfer from one template to another. Anyway, what we've got here is a single drive system, in this case a ball screw, and yes, that would be a Steinmeier ball screw. And on one end, on the left side, you've got a conventional DC motor with a rotary encoder on the back. And on the other end of the ball screw, you've got a rotating piezo motor that's attached with a coupling that connects it and disconnects it. You also have an incremental linear measuring system on the stage itself. And as we said, in this case, we're using a rotary piezo motor. You may have seen piezo motors in this moving fingers principle, primarily used in as a direct linear drive, they also make these similar mechanism, similar system, but it's in this case it's in a rotary system. And this slide here gives you some characteristics. I do apologize if it's a little faint, but again, that's template translation. For this system, we ended up utilizing in this case, a micro-E encoder with a 20 micron scale period with interpolation that lets us get down to resolutions of 5 nanometers. Accuracy is typically on the order of 1 micron. This graphic shows you very clearly what our test setup was, and you can see on the left-hand side the stage is mounted vertically on the left. The DC motor is on the bottom corner, and the rotary piezo motor is on the top. Over here is just a load, and that was, as I said, the test setup. The initial results of the field test here are, here's a graph showing the stage moving in 10 micron steps. And in this next slide shows moving in 1 micron steps. And these graphs are the actual reading from the encoders. So this is actual motion, not necessarily commanded motion. So this basically demonstrates that it is actually moving in these increments. And then finally, the last slide, which shows 50 nanometer steps, and I do apologize. You know, the reason for the nature of the graph is you're seeing mostly electrical noise. So, by way of review, for what we call the dual speed stage, we now have the possibility to create a very, very slow or quite rapid motions with a common drive in a single stage. And the key is that we're no longer limited to only extremely small movements, very slow movements. So that's the key. You have a single system that eliminates the need for the stacked stage approach to this very, very wide speed range that is required, and also the motion basically of being able to move in nanometer motions as well as nanometer per second motion as well as millimeter per second motions. So moving on to some applications, and as I mentioned, it's typically in high-end inspection. This is a machine that's made by a company called Alicona. That's shown on the right side of it, and on the left is a typical measurement that they do. This is some sort of substrate that they're measuring. But anyway, they were faced with the issue that as inspections become more and more complex and parts become larger, they're forced to provide 3D inspection that is greater in many cases or larger than with Z travels that are larger than 1 millimeter, for example, and that's where something like this gets in, would have a great application. And another application would be confocal microscopy. This is a focusing mechanism made by a company that's well known in this industry, PI, and certainly a very fine instrument, but it's quite limited in its Z travel, again, because it's driven by a piezo stack. So remember there, something like this would be limited to hundreds of microns, maybe up to a millimeter, but certainly no more than that. So where the inspection applications, or in this case confocal microscopy, requires motions greater than 1 millimeter, then you have to use some other means to achieve that larger motion before you get into this finer motion. And with this dual speed approach, you don't. You use the same stage for those motions. Thank you.
Okay. Thank you very much. At this point, we are now open for questions. So if anybody has any questions, feel free to type them in, and we'll address them to George. One of the things I wanted to find out is, can you give me an idea of the cost difference between some of the more traditional approaches and this approach, George?
That's a very good question. The first thing I would bounce back with: how many are you going to buy, Leslie? But no, seriously, you know, as was mentioned, I was shown on one of the slides. You know, the typical approach here is the stacked approach. You basically have two drives, two controls, two stages, two individual stages. So stacked piezo stages tend to be costly in any event. So it's a little bit hard to put a number on it. The cost is not going to be half of what you would compared to what someone would be paying now, but it would certainly be the savings would be substantial. It's not 50%, but it's somewhere in between there.
How about the integration of such a system? Is that easy, hard? Do you have things that make it easier to do?
You'd have to. You certainly need a fairly intelligent and adaptable controller, but it's again something that we've been able to do. A lot of the controls now are pretty flexible, and so you know, they are able to switch, for example, between systems if you're dealing with different resolutions. For example, you know, one way, you know, you may have seen on that one slide, you've got the linear encoder, but you've also got a rotary encoder on the back of the motor, and there are, you know, situations where we do switch between one system, one resolution to another. It really depends on the control.
Okay. Question that has just come in. What is the repeatable accuracy when checking multiple large number of the same parts and getting a comparison?
What is the repeatable accuracy? Repeatability, in other words.
Yeah.
Well, if you're down in the let's say you'd be down in the 10 nanometer range, our guess is that your repeatability would be probably on the order of you know, 40, 50 nanometers. I don't know. Maybe Dr. Brahma, I know you're on the line. Are you able to comment on that? I don't know if Alex is on or not. Anyway, I've got.
He's on, but he may not. Yeah, he.
George, can you hear me?
Yeah. Yes. Did you understand the question, Alex? Basically, yeah, a panelist is or an attendee is asking about the possible repeatability on those in that kind of system.
Well, in our experience, it's mainly what we have seen. Is mainly driven by the resolution of the linear encoder. We used to have a 5 nanometer resolution with a noise of plus minus 1 count, and we need plus minus 5 nanometers, and it was possible to repeat this position again and again. That means the stage itself, the drive itself, is able to come down to 5 nanometers. That is what we have seen.
Yeah. Okay. So basically, Leslie, what our experience has shown is that if you based on the smallest count of the encoder, in this case, Dr. Brahma says 5 nanometers, we've seen repeatabilities on the order of 10 nanometers, which is again pretty remarkable when you think about using a ball screw. You wouldn't normally think that a ball screw would be capable of that, but then again, it's a Steinmeier ball screw, so you know, there you go.
Okay. Okay, another question has come in. How does your system synchronize the control of DC motor and Piezo motor?
George, it's okay if I answer?
Yes, absolutely.
For the test, we are using two-axis motion control. That means one axis was used to drive the DC motor of the rotary encoder, and another one for the piezo motor with a linear scale. But that is just an example. It's even possible to combine two DC motors, and so for very specific applications, it's even possible to have one motion control and to switch between both motors. That saves a lot of costs, of course. That is possible. Yeah. Maybe you.
Okay. Are there any other questions from our attendees? Go ahead and type them in.
I think relating back to that last question, it's just, all we can say is that with the controllers that we're using, it is certainly possible to do that. I'm not sure we can answer very quickly how it's done, but it's certainly we've demonstrated that it is possible.
Yeah.
Okay. Well, if anybody wishes to send more questions to the presenters, oops, one more, just here we go, another one.
Okay.
Question came in, single axis or XY? Not sure what that's referring to.
Yeah, I'm not sure either. I mean, the test was for a single axis, but certainly doable for an XY. Essentially, the concept can be modularized, basically. So, yeah, I mean, you could do the same thing on an XY. It's obviously using two motors and on each, using two motors on each axis.
And if you need more explanation, Roger, who asked that question, you can email George, or you can phone him at the numbers that you see on your screen.
Yep.
Any other questions from our audience? Here's another one. What is the maximum frequency it'll handle in a single axis?
Sorry, George, could you explain about frequency in stages?
Yeah, I'm not sure what that refers to. Are you talking about?
Elias, can you elaborate? And he might be typing it in now.
Mm-hmm.
Yeah.
And I don't see any additional questions from him.
I mean, you have to remember that this is that the application. Remember, the application is primarily in inspection. At least the ones we've been that have come to us for the solution. And for that, it's primarily it's a focusing issue. So I'm not sure what the attendee is referring to as far as frequency is concerned, but
Okay.
Sorry.
Oh, here we go. Pushing package to 500 per minute.
Oh, in other words, you're talking about doing multiple moves. Alex, you follow what the issue there is really processing through the controller. I guess it really depends on the type of moves that you're looking at.
Yes, he says he wants multiple moves back and forth. Yeah.
Oh, but that's I'm not sure that's I don't know if that would be appropriate for this again, because this is you know, primarily for it's primarily an inspection situation. I don't know. I don't know that we've ever seen that.
At the manufacturing application.
Yeah, maybe that's what he's after, but I don't know that this would be appropriate for that.
Okay. Okay. Well, if anyone else who's attending has a question, please feel free to email George at gjaffe@steinmeier.com, or you can phone him at the number that you see on your screen. And for those of you who have wondered, this webinar will be available in the next few days online. You will be receiving a URL information so that you can download it onto your system. And we thank you all for attending this webinar. And it'll be available at www.designworldonline.com in the next few days. So thank you, George and Alex, for giving us this presentation.
Thanks, Leslie. Appreciate the support.
Thank you very much.
All righty. Thank you all.